you all for coming. So Amir has planned for 3 lectures. I've planned for 2. So maybe we'll have an early lunch or something. Anyway, so I'll try to break it into 3 parts. So I'm going to be talking about pseudorandom generators for algorithms with bounded memory. So this first part, it's I want to make sure that everybody is on the same page. So I'm going to go over some very basic things. You're basically trying to address the question of does randomness add power to computation, and PRGs, the way we use them in complexity, it's a tool to show that they actually don't. This is very different from crypto, where you're actually trying to do something. Here we're trying to say, no, you can't. So what does a PRG do? It takes a short seed and stretches it into a much longer string, which looks sufficiently random to the class of algorithms that you're interested in, right? And what is the holy grail of pseudorandomness? To just come up with a generator which fools any polynomial time algorithm or small circuit. Take log n bits and stretch it into n bits that fool any small circuit. This would be nice because it would tell us that P equals BPP, that your randomness doesn't add much power to the class of functions that you can compute efficiently. On the good news is there's reason to believe that something like this might be true, because if sufficiently strong circuit lower bounds hold, right, extremely strong, but still the kind of things that we certainly believe ought to be true, then such generators ought to exist. The bad news is that this requires you to have extremely strong lower bounds against the kind of functions that you're trying to fool. This is very easy to see. I'm sure you've all seen it before. Just this is a distribution which is supported on poly n strings. Surely identifying the support of this distribution has to be hard for this class of functions, right? So where does this leave us as far as unconditional constructions go? Well, you could either try and eliminate the randomness that's being used for specific algorithmic tasks, and there are many famous examples of this, and I think one more which we're going to see later in this workshop, which is parallel matching. Or you could focus on classes of functions where somehow this lower bound issue does not crop up. One reason might be that, hey, we actually have lower bounds against them. A more interesting class of algorithms is bounded memory algorithms, and that's what we're going to talk about today. Okay. So, So you could ask the question now, can we construct the kind of pseudorandom generators that we'd really like, even for these two restricted classes? So a lot of the work in this area has focused on these 2 classes. And do we have optimal constructions for these? The answer is almost, but not quite. For bounded memory algorithms which have, say, logarithmic workspace, the best we know is a generator which has seed length log squared n. This has been the case since the 90s. Nissan's result from 1990 got the seed down to log squared n, and since then, essentially, this has been the best. For depth 2 circuits, DNFs, right? Let's not talk about all of AC0, just for DNFs or CNFs, the best we have, again, it's log squared n, this, the same function showing up. Now you could ask, are these the most important open problems here, or are these the most important solved problems in this area? And the answer is both. Of course, this is fantastic, but there are reasons why you actually want to get the right answer. If you get this number down to log n, then you'll prove RL equals L, right, which would be a very nice theorem to have. Depth 2 circuits, so this is somewhat embarrassing, but even for depth 3 AC0, the best lower bound we have is 2 to the root n, right? And this is just because parity is our canonical hard function, and this is exactly how hard it is for depth 3. In fact, we have pretty sharp bounds on what depth 3, what size you need in depth 3 for parity. It's something like 2 to the root n. So really, and there are reasons I won't get into, but which many of you know, to really want to get truly to 2 to the omega n kind of lower bounds, right? And one way to do this, any improvement on this exponent of log squared, if you make it log to the 1.9, you're improving the 2 to the root n bound. So this is one reason why you might want to try and do this. Okay? Okay. Yeah. Yeah, so we'll come to that in great detail. Roughly speaking, it's the support of the generator or its complement, some very simple thing. Yeah. Okay, so let me start by defining formally what it means to have a pseudorandom generator that fools a particular class of functions. A generator is just a mapping which takes s bits to n bits, and it fools a class f of functions with error epsilon if, whenever you take a function in this class, its expectation on a random string sampled from the generator versus its expectation under the uniform distribution are no different. They are within epsilon of each other, which basically means that its behavior on this small pseudorandom set is essentially the same as its behavior on the truly random set. We can talk about expectations because these are just bits. So you have the same expectation, it means you're roughly the same distribution, right? Okay. So now, bounded, as we said, this often having such a strong pseudorandom generator leads to very easy lower bounds against a class. Now, now of course, we know that, one of the hard facts of life in complexity theory is that if you want to prove unconditional bounds, you're not allowed to talk about realistic models of computation, right? You can only prove unconditional bounds against extremely restricted models. This, for me, is the one, striking counter example, it's the exception that proves the rule, I guess, right? RL, it's my opinion at least, a very reasonable class of algorithms which have bounded memory, right? It's a class which we are very far from proving lower bounds for, because TC0, for which we don't know lower bounds, is contained in NC1, is contained in L, is contained in RL. Now, we can debate about how many of these inclusions are strict and how many are not, but the fact remains that we are at least one solid lower bound away from proving anything about RL. So how come we are able to construct unconditional pseudorandom generators for this class? It has to do with the model. So what is a Logspace algorithm? It's a Turing machine which has an input tape. It has logarithmic workspace. But rather than thinking of a random tape, it just has a coin which it can toss. And now, if the algorithm wants to remember what the coin tosses have been, there's no free lunch. It needs to write it down on its workspace, which is only log n bits, right? So another way to think of it, since we are used to thinking of Turing machines which have random tapes, is to think that you have only one-way access to the random string, right? I think it's just more natural to think in terms of flipping a random coin. And this one-wayness is what makes all the difference, because it's not that you have a Logspace algorithm which is really given a string and it can do whatever computation it wants and try and identify if this was generated by the PRG. You should think of this more like a streaming algorithm where it just makes one pass over the input. It has logarithmic workspace, and now it needs to tell whether this is a truly random string or a pseudorandom string, right? So this is why, despite this being an interesting class, you can actually hope to prove an unconditional statement about it. And the other thing which is nice about RL is that you don't need to talk about Turing machines at all. It has a very clean, non-uniform model, which is bounded with branching programs. And we're going to be focusing on branching programs throughout this talk. What is a branching program? Well, think of it as this kind of a layered DAG. So it has some number of states at each layer. We'll think of this as a parameter W, which is the width of the branching program. And then N is the number of and then there is N, which is the length, right? So you should think of this as the number of random bits that the branching program is going to consume. It starts off in some state, and instead of random bits, it will often be convenient to think of random symbols over some alphabet M. So it makes a transition on M, and then again it gets the next random symbol, it makes a transition, and finally it reaches some final state based on which it's going to either accept or reject, right? So it's like non-uniform model of Markov chains, if you will, right? If this was a really Logspace algorithm, the transition diagrams would basically look the same for each and every layer. So we can just take this as our model, or we can just very quickly talk about why this captures RL, right? So you should think of N as roughly the running time. It's basically the number of random bits that your algorithm consumes. The width is the total number of configurations that your Logspace machine could have. Now the configuration is basically going to be the position of the input head and the contents of the work tape. So if you're using Logspace, then you'll get polynomial width out here. And things like the input, specific, the real input, and then the logic of the algorithm all gets encoded in the transition diagram here. For instance, if you're thinking about a random walk on a graph, then imagine that it's an M regular graph. So what is this transition diagram going to look like? Well, it's just going to be, you're going to have the same graph in every single layer. You're just taking a random walk on it. If you change the graph, then the transition diagram will change. Okay? So these are the parameters that we need to keep in mind: the width of the branching program, the length n, and the alphabet m. Okay, good. Now let's ask the question, what is in this class RL? So I've told you that it's a very interesting class of algorithms. Is that really the case? What lies in this class? Well, one thing we all know of is undirected graph connectivity. This was in the 1970s. Linus et al. Proved that the random walk algorithm solves undirected graph connectivity in randomized log space. It's complete for a class SL, a subclass of RL. You don't need to know what that exactly is. What else is in it? Well, in some sense, this is the only superstar in this class, okay? And we actually know that this is in L. We all know that by now. So why is it still interesting to de-randomize RL? So I think the main reason is a lot of the brick and mortar kind of things that we use randomness for in algorithms, they actually happen to fall in RL, right? A lot of things, what you'd call simple statistical tests. So this, I guess, is it's more a statement about the way that algorithms typically use their random bits. They typically use them to do some simple kind of hashing, random projection, rounding, and so on and so forth. And it turns out, with appropriate massaging, if you think about just how the randomness is being used by the algorithm, a surprising number of algorithms, you can see them as being, you can fit this model of log space with one-way access to the randomness to these things. So this point is made very nicely in this paper by Shivakumar from 2002, where he points out that even things like maxcut, the Gomez-Williamson algorithm, this is an algorithm which solves SDPs and so on. I don't think there's much hope that at least this algorithm is ever going to be done in log space, but it doesn't use randomness until it comes to this randomized rounding phase, right? It just, it has these vectors and then it takes a random hyperplane cut. And what he says is that if you do things right, you can think of this process of just doing the randomized rounding can be done by the kind of log space algorithm that we have in mind. So Nissan's generator would fool this test. Right? So really, the point is RL is pretty ubiquitous in some sense. A lot of the things that we want to do, like hashing, rounding, churn off bounds, these kinds of tests, they fit very nicely in RL. So in order to de-randomize RL, you need to be able to de-randomize these very simple uses of randomness in algorithms, right? Okay, so what do we know about RL? As I said, Nisan gave us this generator with seed length log squared n. It's been a really long time since that happened. He actually did something even a little better than that. If you have seed length log squared n, this implies that you get a deterministic simulation of your algorithm in time n to the log n, right? But he observed that you can actually do better. He said that, okay, so this generator actually requires log squared n random bits. But if I know what algorithm I'm trying to fool, like let's say I know its graph connectivity, then I can cleverly set most of the bits in the pseudorandom generator deterministically, all but log n bits, okay? This takes log squared n space to do, but the upshot is that you get a polynomial time simulation rather than a quasi-polynomial time simulation, right? So this puts it in this class SC. Then Sachs and Zhu showed that actually you can do it in space log to the 1.5. This remains the best that we know currently. And this, for me, the really nice thing about this is that it has found a lot of applications in algorithms where you really don't care about conserving randomness. The resource you're interested in is something else, like in streaming algorithms, it's space, right? And it just turns out this is a very versatile tool which applies in a lot of surprising settings. Like I would say that Nissan's generator, at least streaming has moved on, but in the early days it was the heavy hammer of this area. And finally, there was this beautiful breakthrough about 10 years ago now, where Reingold showed that SL equals L, basically giving a deterministic algorithm for undirected graph connectivity, right? And by because it's complete for this class, anything which is in SL, we can de-randomize. Now the question is, what remains? And so, of course, improving this bound has proved elusive, but even for these very annoyingly simple statistical tests, like, my algorithm uses a Chernoff bound. I don't care exactly the details of what it's doing with the Chernoff bound. I should be able to de-randomize this, right? Even for very simple statistical tests, this proved to be fairly tricky to do, right? Or, just say that the algorithm takes summation ai xi, looks at it mod m. If m is a prime, a small prime, we've known how to do this since the work of Nauer and Nauer. What if m is much larger? Say it's around root n, right? We didn't know how to de-randomize tests like this, okay? So the main focus of today's talk is going to be this thing, which I call the gradually increasing independence paradigm. It's basically an iterative technique for constructing and analyzing pseudorandom generators. I would trace its origins to these two papers, which appeared more or less around the same time. There was this paper by Kane, Mecca, and Nelson on de-randomizing the Johnson-Linden-Strauss lemma, and another paper by Sellis, Reingold, Weider, and Segev on basically de-randomizing certain kinds of hash functions for load balancing, which introduced this general idea. And since then, it's proved to be a fairly, versatile. Basically, it's a new technique for constructing PRGs, and these are very few. We have about 3 or 4 of these, right? It's proved fairly versatile. It basically, we'll talk about this in more detail. It fools a lot of these simple statistical tests, which we really thought, this has to be easy to fool, but we just had no idea, in many cases, how to improve on Nissan's bound.
Just to clarify, so when you say that you want to fool lemma bound, you want to somehow sample things not independently, but
Yeah. Yeah, exactly. Yeah, so what does the Chernoff bound do, right? Usually it takes a sum of random bits and says what is the probability it's going to be like, greater than root n times some constant. Instead of something like e to the minus c squared, right? So you want to fool this, let's say, right? So these kinds of things comes up in discrepancy and so on, right? I'll be more precise about all of this. This is, yeah. Okay, and typically the seed lengths you get from this are they are up to these lower order terms. They are logarithmic in n and epsilon. I'm going to ignore log n terms throughout this talk. The new polynomial is log n, so we're interested in gaps between log and log squared. We don't care about log terms, okay? All right. So here, since I had to fill up 3 hours, I said that I should, since there's supposed to be 3 lectures, there should be 1 lecture which absolutely everybody understands, including even the speaker. So I'm hoping it's this one, As Yishai said, this is going to be a walk down nostalgia lane for him. I'm going to talk about Nissan's PRG, but focusing on combinatorial rectangles, which is a special case of branching programs. So maybe you've seen Nissan's PRG, but you've never seen it presented so narrowly before. So that'll be something new. And then, yeah? And then I'll talk about the gradually increasing independence paradigm. We'll talk about hash functions for load balancing, and then combinatorial rectangles, whatever those are, and read one's CNFs. Yeah, we'll come to it when we come to it. Okay, so let me start by introducing combinatorial rectangles. This is going to be the recurrent theme of this talk. We're going to come up with optimal generators for these and then generalize them. What are combinatorial rectangles? Imagine that you have n bins. Each bin contains m balls, okay, numbered 1 through m, of 2 colors. Some are black, some are white. Okay. Now the interesting event for you, maybe you get a prize if you draw a ball from each bin, and then all the balls happen to be black, okay, or white if you prefer. So if we do this uniformly at random, do independent sampling from each bin, what is going to be the probability of all the bins being black? Well, here if the fraction of black balls is P1, here it's P2 and so on, then it's just going to be the product of the PIs. And now I'm interested in constructing a pseudorandom generator, a much smaller set of strings in m to the n that fools this very simple class of tests. So once again, I know that there are two colors of balls, but the bin is opaque. I don't get to see when I'm drawing which color, which ball is which color. Ishai?
So, just to make sure that I understand.
Yeah.
Okay, you have a combinatorial rectangle, and what you want is a set of points which is approximate its volume.
Yes, exactly. Yeah. So what I want is exactly what Yeshai said. So let's formalize this a little. For each coordinate, I have these functions fi, right, which just give you the coloring of each ball. Is it white or is it black? And now the function I'm interested in is the product of these functions, let's say, because the function is 1 if it's black, and the function I'm interested in is what is the event that all the balls are black. So it's just the product of the fi's. And when I do this uniformly at random, the probability that all the balls will be black is just given by the product formula. It's the product of the expectations of the xi's, of these fi's, right? So if each of these is 1 with probability pi, then it's the product of the pi's. So constructing a PRG for combinatorial rectangles, it's asking this question which seems extremely basic to me. When we use this product formula for expectations, we typically use it when the inputs are really independent. Does the product formula require true independence, or can you de-randomize it? Right? So this is why I think this is a very clean formulation, and it's also something which is very ubiquitous. It comes up in a lot of other settings. Okay, so I think now, okay, what is known about this? Well, this is a very simple branching program. So Nissan's generator, of course, fools this class. And these are very closely related to a notion known as minwise independent hashing. So people who were trying to construct minwise independent hash functions were more or less, they were doing the same thing that people in the PRG community were doing. There's a result of Even et al. From 1992 and a result by Piotr Indyk from 99. Both of them basically say that if you want error epsilon, then it suffices to pick your inputs, which are log 1 over epsilon wise independent. Okay. Lu improved this dependence to log n plus log 1 over epsilon to the 1.5. And finally, fairly recently, we gave the right dependence with what I consider to be a fairly simple generator. Okay. So we're going to see this eventually, but right now we're going to talk about Nissan's generator, right? The bare bones version of Nissan's generator, which, Nissan probably never considered doing something so basic with this, so simple with this generator, but okay. So let's start from the case when n equals 2, okay? So what are we trying to do here really? We are working with m cross m. So it's natural to think of m points on either side, okay? And now we want a set of pairs, right? It's very natural to think of these as edges. What is the property that we want? What are the tests we're trying to fool? Well, a rectangle here is just a subset A on the left, a subset B on the right. The property we want is that the fraction of edges between A and B, the fraction, is roughly what it would be if you were throwing in edges independently, which is mu A is the density of A, it's the size of A over M. Mu B is size of B over M. You want a graph where the density of edges between A and B is roughly mu A times mu B, right? And we all know how to construct these graphs. This is exactly what an expander graph will do for you. If you pick a graph whose second eigenvalue is lambda, then the bound that you'll get is something like lambda over D here. And by picking, if you take a Ramanujan graph, then lambda is bounded by root D. So, you pick degree, which is roughly 1 over epsilon squared. So the case of n equals 2 exactly corresponds to expanders. Okay. Now you could try and generalize this to the n-dimensional case. If you actually do it right, you'll get something known as the Impagliazzo-Nisan-Wigderson generator. If you do it, but it requires some clever idea there. If you do it wrong, your seed length will blow up and you'll get a generator which shrinks n squared bits to n bits. There's nothing wrong with that, but maybe there are ways to do it without Ramanujan expanders. what I'm going to show you is Nissan's original construction, which basically does this just using pairwise independent hashing. Okay, so all right. So the key lemma there is this very simple lemma, which a lot of you have seen before. It's known as the, is there an, yeah. The key lemma is what is known as the hash mixing lemma. So this is known as the expander mixing lemma. What does the hash mixing lemma say? It says pick a hash function h from m to m from a pairwise independent family of hash functions. The simplest example is that if m is prime, you can just do ax plus b, right? Okay. And now here's what it tells you. So once you pick a hash function, for each element on the, it basically gives you a matching between the left and the right. For each element on the left, you have some hash image on the right. So here's what the guarantee is. The probability over the hash functions of the following quantity, which is the quantity we really care about. When I pick x randomly, what is the probability of the event that x lies in A and h of x lies in B? Right? I'd like this to be mu A times mu B. And what this lemma guarantees is that the chance that this probability is off by more than epsilon is less than equal to 1 over epsilon squared times m. Oh, okay. Okay, yeah. So this is what, so let's just go over this statement once again, right? Let's fix a hash function m. It just gives you a matching from the left to the right. Now what you're interested in, fix a test. You're interested in what is the number of edges that go from A to B. That's exactly what this thing counts, like in the previous case. And while in expanders, you're guaranteed that for every A and B, the deviation is small. Here it is a probabilistic guarantee that for most A and B, the chances are, if you take this m to be large enough, that this hash function will actually work. Okay? So, how many people have seen the proof of this thing before? Okay, that's not as many people as I would think. So then I'm going to do the proof, and if you've seen this too many times, you can shut your eyes. Okay? So this is just a basic example of pairwise independent sampling in action, right? So once I fix, let's think about fixing a hash function h. What it basically gives me is for every, it basically gives you a matching from the left-hand side to the right-hand side. Now here is my set, let me make this slightly bigger. Here is my set A, right? And here is my set B. There's going to be some subset of things in A that are matched to B. Let's call this subset S, right? Now, once I pick my hash function, there's only one thing to do, which is to pick x randomly from the left-hand side. If it lands within this set S, then you have both your conditions satisfied. You are in A, and your hash is in B. So the event that we're really after, this probability, let me call this P sub h, because it's a function of the hash, right? P sub h is simply the size of S divided by M, because S is the good set. If you land in S, then you satisfy both your requirements. Okay, so what is the size of S? Well, I can write the size of S very simply as a sum over points in A, I of x, where I is the indicator of the event that the hash maps this point to something in B, right? And this is where we're going to use the pairwise independent. So size of S is this thing, okay? So now the random variable we care about is size of S divided by M. So this is, we've called this PH. What is the expectation of PH? Well, it's the sum of these IX's. Each of these is a Bernoulli random variable because it's a pairwise independent hash function. Each x is going to land in the set B with probability exactly mu B. So the expectation of this is going to be A times mu b divided by m, which by strange coincidence is mu a times mu b, which is exactly what we want it to be. Okay. Now, what is the variance of this random variable pH? So pH is a random variable depending only on the choice of the hash function. What is its variance? Well, it's very easy to compute the variance of a sum of random variables which are pairwise independent. This is where we're using pairwise independence. It's just going to be the sum of variances. And then because we have the scaling factor of m, we'll have to divide by m squared because that's how variance works. So, sorry, is this going too low again? Okay, so maybe I'll continue on this side. Sorry, yeah? Oh, okay. So what is the variance of pH? Again, each of these ix's is a Bernoulli random variable with expectation, which is 1 with probability mu b. So the variance of these kinds of things is just a times something like mu b times 1 minus mu b. And then you have to divide by m squared. Okay? And so you can rewrite this in a more symmetric form as mu a times mu b divided by m. I'll ignore the 1 minus mu b term because we are interested in an upper bound on the variance. Okay, great. Now that we have the mean and variance, we can talk about what is the probability. We'll see a deviation of epsilon, and just Chebyshev's inequality tells us that the probability over the hash h, that pH minus mu a mu b exceeds epsilon, is less than the variance divided by epsilon squared. There's this mu a mu b term which we are getting. I'm going to ignore it. It's less than 1 over epsilon squared times m. Okay. So this is the proof of the hash mixing lemma. As you can see, it's literally just a couple of lines. It's surprisingly powerful though. So now we're going to use this to first construct a PRG for rectangles, and then from there get a PRG for bounded space algorithms. Okay, so let's do the rectangles case first. Okay, maybe let me go to the other side. Okay, so now we are in n dimensions. Okay, so these coordinate 1, coordinate 2, coordinate n minus 1 through coordinate n. So what we do in the first stage is that we try to reduce the dimension, call this parameter the dimension. We'll try and reduce the dimension from n to n over 2. How will we do that? We'll pick this one hash function h and use it to match up all pairs here, right? So what do I mean by matching up? If you pick x here, then from this rectangle, you'll pick h of x, right? And you'll do this in all these n over 2 rectangles. You match things up. Now you hope that this hash function h that you picked is simultaneously good for all these n over 2 rectangles. The probability of that happening, it's not too bad. By the union bound, it's going to happen with probability something like n over epsilon squared m. With this probability, what happens is that all these new the probability of x lying in A and h of x lying in B is what it should be. It's mu A times mu B up to a certain epsilon, okay? But once you fix h, you've reduced the dimension of the problem to n over 2, because this is essentially now a problem exactly of a combinatorial rectangle in m to the n over 2. Why is that? Well, really now, while previously we were thinking about, the balls, the vertices having colors. Now, once you fix the set A and B, you can think of the edges as the things that you're sampling. And the good edges are exactly the ones which go from A1 to B1 and so on, right? So in essence, we've reduced this to a problem of sampling from a combinatorial rectangle, again with an alphabet of size m, but in n over 2 dimensions. We paid a little bit in the error because these are not exactly the same. The probability of this new combinatorial rectangle, it's the probability of this being 1, its volume is off by some epsilon times n over 2. You can prove this in a number of ways, okay? But now we're just going to recurse. For this n over 2, instead of sampling truly uniformly independently, we'll pick another hash function which will reduce the dimension to n over 4 and so on and so forth, right? So finally, the recursion is going to, okay, so how are we going to set our parameters? So one thing I didn't say at the outset, and I'm going to say now, is that it's simplest to assume that m is pretty large. Assume it's something like n to the 10. The case of m smaller alphabet is never a problem. You can blow it up, right? So assuming that m is something like n to the 10, how are we going to set our parameters? We're going to set this epsilon parameter there to be something like 1 over n squared, let's say, because finally we have to union bound over something like n squared rectangles. We don't want the final, it's n log n rectangles. We don't want the final error to be too large, right? So what you basically do is you take epsilon to be something like 1 over n squared, and now provided m is something like, so this is the interesting thing here. Even if finally you only cared to get an error like something like 1/10, because of the union bound over all these rectangles, you'll have to start off with this error parameter being polynomially small in n. So to this generator, it doesn't really matter whether you're going for constant error or 1 over poly error, the parameters will basically be the same, right? Yeah. So here it's order n in this one level of the recursion. Yeah. Okay. It's not even n log n. Maybe it's n. Good. Okay. So, yeah. I mean, I was even willing to give n squared here. It's not going to help you much. Okay. So basically, we're going to take, if m is something like n to the 10, then how many bits does the pairwise independent hash function require? It requires log m bits, which is, so m I'm going to take to be something like n to the 10. So I'm going to spend log m bits at every stage, and then there are log n levels of recursion, right? If you do things correctly, you'll get a seed length, which is log m times, you'll probably have an epsilon somewhere here, and so on. Okay? So basically, it's a very simple dimension reduction kind of idea. At each stage, you just reduce the dimension by half. And going from here to branching programs, it's basically just, many more rectangles enter the picture, but that's it. So let's try and apply the same idea now to construct a PRG for branching programs. So the idea, okay, so there's one thing. So this is why in branching programs, it's nice to think of this alphabet m as something possibly large rather than just 0, 1, which would be arguably more natural, right? So let's think of a branching program where we look at the input in chunks of size something like 100 log n. So intuitively, for this generator to work, so what is this generator doing? It takes a truly random string of length 100 log n. It hashes it. Then it takes another truly random string of length 100 log n, and then it applies the same hash and so on. So if this 100 log n was something like log n over 10, this generator couldn't possibly work. I have enough space to see if what I'm getting is actually, so the first time I see this, I'll say, I think this is the hash function which is being used. And then I'll check it, and if the second time I see the same thing happening. So to really work against Logspace, you expect that, you at least invest 100 log n random bits so that the algorithm cannot just do the obvious attack on this generator, okay? All right, so how does the generator for bounded space algorithms work? So let's just consider the first two layers. We're going to collapse this down to one layer using a hash function. And here's what we're going to do. We have all these states. We have this alphabet of size m, right? So it's seeing inputs in blocks of length, something like 100 log n. So again, you're going to hope to use x here, and then h of x here, then some new string y here, and h of y here, and so on, okay? So let's just consider a path from some state I here to k via an intermediate state j. What is the set of strings that takes you from I to k via j? It's essentially a rectangle. There is some set which takes you from I to j, and then there's some other set which takes you from j to k. It's the product of these two. So if the hash is good for this rectangle, then okay, you'll get from I to k via j with roughly the right probability. Well, now let's talk about all possible intermediate states. That's only n rectangles. So let's assume the hash function is good for all these. then the probability of going from I to k is roughly what it ought to be. And then we'll go over all k. So now it becomes something like n squared rectangles. But then all the transitions out of state I are correct. Let's talk about all i's now. If you're keeping count, it's n cube or something like that, right? So now all transitions from this state to this state are roughly within the right. So the error is actually adding up, but it's not too bad. It's becoming epsilon n squared or something. Okay. So now let's do the same thing for all these n over 2 layers here. Let's assume this one hash function is going to be good for all of these. And some n to the 5, n to the 10 rectangles that you need to fool. But once you're done with that, again, like in the case of rectangles, you manage to squash the branching program from width n to width n over 2, right? Because once h is fixed, when you see your input, well, you're going to land up at some state here. How you actually compute that state is to say, okay, I go here, but it doesn't really matter. Essentially, it becomes a transition diagram on an alphabet of size m of length n over 2. So essentially, the same kind of recursion will work out. You keep careful track of the errors and so on. You'll get a length, again, which is something like log n times log n over epsilon. Okay? All right, good. So any questions about this part? So, yeah, Ishai.
This is probably most about lecture. Did you really use the fact that you're sampling over the uniform distribution?
Uh-huh. Well,
You can do an outlier distribution.
so you're saying, does this work for general product distributions?
Not so that, right? Because like a busy dimension argument would say that you don't need many samples in order to approximate the volume
Okay.
with respect to any density.
With respect to any density. But, okay, yeah, but you want a distribution which mimics, small support distribution, which mimics the density of the uniform distribution.
Right, no, I understand what you mean.
Okay.
Can we mimic any distribution? So you need to define how am I giving you this distribution. But
I see.
But if the image of the PRG is a small set, the final distribution.
No, but maybe maybe the technique will be tailored to what distribution you're trying to fool.
you need like an option saying how do you generate the general distribution? Alright, so when I give you distribution,
Yeah, it's not for Wolf's distribution, you put in something for the distribution. Or the PRG can.
I think Ishai's.
you tell me what you want to assume and I'm willing to buy it.
So I think. So I think Isha is saying that it's not about this generator, but this technique might allow you to estimate volumes under more general distributions.
Having small number of points estimating the volume
Right.
has nothing to do with uniform distribution.
Sure. Fair enough. Yeah.
So I'm just wondering what in this pseudo-random generator is very tailored.
Oh, maybe it's about the explicitness, right? I mean, you know that a random set of points, any random set of strings in m to the n is going to be a great PRG, not just for volumes, but almost any class of functions with small disk. It was all about the explicitness here. Okay. We'll talk offline, yeah. I don't see the answer to your question, maybe. Okay, so let me just tell you, in a vague and my description of combinatorial rectangles was somewhat concrete. This was vague, and now even more vaguely, let me tell you how Nissan's RL is an SC result works. So for this, you don't work with branching programs. You actually assume that you have a Logspace algorithm. And the basic idea is this. You're trying to sample a random function h, which satisfies certain goodness, right? Which is that it fools a certain number of rectangles. We know exactly what rectangles we want to fool. His observation was that, hey, if I have a candidate h, then I can actually check this condition without too much blow up in either space or time. Because suppose you give me an h. I know that these are exactly the set of these are exactly this, fix one rectangle here. If you can do one rectangle, check that h is good for this rectangle, then you can do all rectangles, right? Now, what are we really trying to do? We're trying to say, well, if I take two random strings of length 100 log m each, what is the chance they take me from I through k via j? Versus if I use x, hx, what is the probability that they land I go from I to k via j. You're just checking that these two numbers are within epsilon of each other. And this, there's no reason you need more than log space and polynomial time to do this. Okay? Okay, so now you fix your h. What this does for you in the next step is that the description of your program becomes slightly more complicated. Because now what happens is you give it a string x, run the program on this, then you hash the string, run the program on that. But fine, it can still be done, you know, in Logspace. The actual dominant space requirement comes from keeping track of log n many of these hashes. That takes log square m space, but overall you can do this in basically log squared m space and polynomial time. What this is giving you is in this distribution of size n to the log n, tailored to the specific algorithm, you found a subset of polynomial size, which actually looks pseudo-random, right? It's not one PRG which is oblivious to the log space algorithm. It's kind of a nice subset of Nissan's PRG, which works well for this particular log space algorithm. Okay. I'm sorry?
It seems that you just pick the age.
Oh, just yeah. This you just cycle over all h's. No, the h is just enumeration over all h's. You know, before too long, almost every h will be good. So you'll find one. Once you've found one which is good for all these rectangles, fix it and keep going. Yeah. Yeah, the RL is an SC paper. I think it's again a beautiful paper. The thing is, the algorithms are actually written as code. So I think that this is something which is actually one of the nice things in Shivakumar's paper was that he seemed to really understand what was going on, and he said, oh, this is amazingly general. You can apply it in a lot of settings which have nothing to do with log space algorithms. Okay. All right, so I think it's a good time for a break. We can come back or not, whenever, and we'll continue.